let's get rolling. Couple reminders. So just quick check. Did everybody try to log on to the Canvas site? Works? Cool. Everybody able to access the YouTube video? Try that at least. I'm trying to make sure that it's properly linked and stuff. Give it a shot. Like it should be okay, but feedback. If you're not able to access it, please let me know. All right, we left off last time introducing rate expressions. Again, this is mostly review from everything back to Chem 123. And again, big wall of text. This is meant for your reference for parts that you've definitely been through. Specifics, right, is we left off here. Now remember, this what we're talking about is the rate of consumption of something, rate of formation. They're related by the stoichiometry. This is really mass balance, and this is how our first pass for figuring out anything to do with is this overall equation complete. So if you see an equation like this where we've got some transformation, the stoichiometry should predict what the mass balance is at any point in this, where we're taking the individual tangent and rate of the curves that we've got. If it doesn't, right, if we have any chunk of time where that last equation is not true at every point in here, we're missing a component. There's an intermediate that's not being seen, is usually what we would see. The other part that I want you to highlight too is, well, again, open question. What if this was the correct mechanism? What if there are no intermediates, but the mass balance doesn't line up? What's wrong? If you had, again, put on your problem-solving hat. What else is going on here that for some reason, mass balance doesn't seem like it's matching up? In other words, you take the individual sum and concentration of every step, you're trying to make that this equation is true, but it does not seem to be true. What would you point to? Who do you blame? Intermediate. What if it wasn't an intermediate? You're right, intermediate's first one. Give me another, what else you could do? Yeah.
Branching reaction.
That still starts talking about like other products. These are things thinking that this equation is not true and you're looking for other actors, right? I'm putting back that may be not the case. There are no other actors. There's no third man on the grassy knoll, whatever. What else is wrong?
Maybe it's something leaving the reaction vessel.
Still, that's saying they're still missing. No molecules and no atoms are missing. Again, those are all the right ones to go to first. What else? There's something else. Heat would not necessarily mean that your concentrations are off. Maybe your rates are different. That's the way the reactions wouldn't work the same, right? But back to, again, the main question I'm asking is why might mass balance not match up even if there are no missing reagents, missing compositions? And it still sounds like something's leaving, right? But you're getting closer. Now you're starting to talk about the measurement is off, right?
Measurements tend to be of activity rather than just concentration, so maybe something is under-reporting due to that.
Or even maybe your calibration curves are wrong, right? But that's the direction I'm kind of saying this. Remember, there's two things you're always trying to do. This curve right here that you get, we often take this as ground truth, right? And now you guys are 4th and 5th year, right? You live in a world where the measurement you make is now circumspect to both your technique, your ability, the calibration of the system, who was on it before it, who cross-contaminated your system, whose glass vial you were using that had another material in it that you didn't expect. All of those are things that you need to start looking critically at your data. So part of the thing too, and this is just it's a focus of something called Occam's razor. You guys have heard this before too, right? Sometimes there's no magic. Sometimes it's your calibration is off. Your diode array is dying. You do have to bring that back into your focus because there are times, especially you graduate students, you may spend 4 years because somebody didn't clean your vial properly, right? So you do have to go back to some of the simpler solutions too. I always remember that, right? The data that we have here has gone through a process or a transformation, and you have to make sure that that's something else that you bring on your point. Anyway, in general, things that affect reaction rates, why reaction goes faster or slower, these are usually the ones that we talk through. And again, this is assuming what I mentioned before, that your measurement is absolutely accurate, but going through things like, okay, what is the nature of the material, the physical states, gas, liquid, solid, how they contact each other, right? There's rate constants to do with dissolution or phase behavior. There are individual concentrations, and again, we're always dealing with things like concentrations. That's the gas, fuel, or how much something is, right? Generally, things will respond to this, and this is what we talked about order. We're really talking about the concentration dependence on the rate. Temperature, obviously that's Arrhenius, activation parameters. Catalysts are different mechanisms. Solvents really have these broader sort of pieces to it. We'll talk a little bit about each of these as we kind of go through how we might tune and affect them, but this also goes back to reproducibility. Getting a reaction to do the same thing means nailing all these parameters at the same time as well too. We talked briefly before, rate laws. Now, when we talk about a rate law, we're trying to do an expression that says, based on things I can measure, this is probably what I would see at the rate. And we're talking about instantaneous rates at this time. Like if I could zoom into a reaction and I knew its rate constant and the concentrations of those twos and those orders, I can tell you how fast it's going to run at one time. Why might that be useful? Like why, if this is true and I had this equation, how might you apply it?
You compare it to other reactions.
Okay, so when you do that, what are you doing with that? Like what
Figuring out which one is quote unquote
faster, slower? Yeah, that's one. You can you're categorizing or fingerprinting it, right? So different reactions with same concentration may have different Ks associated. So this is like which catalyst is better. Yep, that's good. What else? What's a practical reason for having this?
Determining how long to run a reaction for.
You want to know when you can go home, right? Like but seriously, that's it, right? The purpose of this is I'm setting up and looking at a plant, and I've got this much stuff I have to turn into product, and that's my rate. And you want to be able to look at this and say, cool, that's 72 years. This is not a decision I want to make, right? Usually you're making this is what you choose for reactor design, what temperature you're going to run it at, because you have finite, in this case, delivery of the material is the finite product you're running forward, and using something like this tells you, do you have enough physical hours in the day to do this part, right? There's sometimes a reaction will require you to do something, intervene, and then do something else. Anybody who's in the Chem space, you know this, lithium, like a lithium enolate generation, or if you're doing a cross-coupling and a deprotection, there's a step you have to intercede at some time. If you knew the rate says, I have to come back to this at 4 a.m., maybe you should plan when you're starting this so that this can match out, right? So this is a practical application of these points. In the end, remember, the rate has nothing to do, these stoichiometric constants are not the same thing as your exponents, or what we'd call the orders in this case. It's just an expression that talks about practically how the thing is going to behave under a certain set of conditions with a certain catalyst. So they're not the same thing. You can't go back and forth between the two. Rate constants are unique. Does anybody have a couple basic rate constants? Like, do you have a sense of if I tell you a reaction is diffusion limited, what's the size of that in terms of magnitude? Are we talking like 100 moles per second? Like, do you have a sense of what these numbers look like?
Times 10 to the 8.
Yeah, you've probably heard something like 10 to the 8. Okay, what's the unit of that? See, we'll get back to this because remember, rate constants, in the end, rate will always be expressed as moles per second, right? It's some concentration per time. It's a concentration over a time point. Over here, these are all in what unit? Not an equate, yeah. They're moles, right? You've got concentrations here. This must be concentration per time. The rate constant will change its unit so that those two things are true. In other words, depending on how many terms over here you may have divided by concentration, divided by something else. Usually, the time piece has to come from rate, so there's always going to be a per second associated. But you may have just per second if it's first order. It may be concentration per concentration second if it's second order, right? Depending on how many terms you have over here, it's moles, 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 moles. The rate constant sort of acts fluidly to make those two sides of the equation, units at least, true, right? It's always going to match those points. But instead, yeah, 10 to the times 10 to the 8, 10 to the 9, that's kind of diffusion, right? What would you call a slow reaction? Again, anybody who's ever done enzyme kinetics, you might have compared rate constants of certain processes, and we kind of use those as fast and slow. It's okay if you don't. It was more just how fast does something happen if you're talking about dissolution or solubility. Kind of grounding this is useful to have because this helps us to rate the thing of what is fast and slow. And we'll talk a little bit more about those in a couple spaces. Orders, we said before, it's the exponent. It's just the empirical rate law that says if I double this, what happens to rate? It's that unit part between it. That's truly what order is. We're going to dive into a couple papers. A colleague of mine whose name is Jordi Burris, he came up with this technology or technique called variable temperature, or VTNA, variable time axis normalization. It's a way of sort of visualizing rate constants and mechanistic development that doesn't mean you have to go down to the full math. But he wrote a really important paper called What is the Order of a Reaction, right? And the problem of this is because it's a bit abstract. And we'll talk about this a bit more today. So yeah, numerically, the definition is the order of this reaction in A is given by that exponent. The overall order is the sum of these exponents. Has anybody ever impacted a reaction? Like usually, what is the value of M and N? What would you typically normally see? Most commonly, these are probably 0 first, right? Anybody seen a 0.2? You have, because this is what we get to play with. The order can be any number. Any number, it doesn't have to be an integer. Because remember, what we're showing here is the power law form, and it's derived by saying I took a reaction at some condition, I made a measurement that really said if I double this, what happened to the rate? Now first just means doubling one doubles the other. Great. But there are cases where if I double something, the other one changes, but not fully 0 and not fully 1. Fractional orders are possible, and we'll get into why that is because remember, this is not a mechanism. It's a mathematical representation of what happens if you turn these numbers. It's what we call the driving force. This is a way of looking at this reaction saying, if I need this thing to go faster, and if this order here was 0.1 and this order was 4, well, screwing around with A is going to make it go faster a lot better than B. Messing around with this to a low order means it doesn't really care what that concentration is. It's not going to impact the rate of the reaction. But if this here had a high power or high order, that's a way that I can have a meaningful impact in terms of the rate without changing temperature or without changing mechanism, right? So it's a sensitivity of the rate to the overall process. So, big reminder, these are empirical. You cannot pull them out just from here. This has to be something you measure, and it's something we mentioned last time. The most common one you've probably seen before is the method of initial rates. That's the one that you usually are introduced to as a way of actually extracting these ones. We're going to go through this in more detail. As a reminder, how we do it is we say I'm going to take the initial part here. I'm going to measure the rate of the reaction, so it's a change in concentration at some change in time. Now, as we mentioned last time, when we say fast or slow, these are arbitrary parts. We're saying, in general, best practice says we want to measure the most accurate change in concentration possible in the smallest time interval possible. So we want to be able to look at this early part of the reaction, know when we started it, know the concentration at that time, have some period of time elapse, know exactly how much time has elapsed, and know the concentration there. And that will completely depend on your system. There are some reactions that in order to get that concentration measurement, pulling the aliquot may take you 5 minutes of physical time to do that. If you use NMR, so again, timescales, what is the approximate time scale of an NMR measurement? Like, can you measure things on the seconds time? Yeah, you know, how fast is a radio pulse, right? But if you imagine, like, has anybody done like time course NMR, like multiple signals? What's your usual spacing between like one sample and the next sample? How much? A couple minutes. Why do you set it that way?
To get numerous scans to get anything that's actually useful.
Well, but that's an interesting point. So a bit of a divergence. But yeah, what we're talking about here is that rate determination you're going to run into, you need a way of getting that number, and you need precision and accuracy of whatever this is, and you're calling that t equals 0. We're assuming at that time that if I didn't do anything, this would not change. So implicitly, my t0 has to have a constant value way back before I'm saying the reaction starts, before I really call this, right? I'm assuming that I know how to start this reaction, and it doesn't look like this, right? Otherwise, it's a call. To your point of multiple scans, well, each scan takes, you know, let's call it 3 seconds, right? Your delay time on an NMR is a couple seconds to allow it to ring down. Well, if I've got 3 seconds, and this is changing fast enough, if I take 4 scans and I average it, what's the concentration I'm actually measuring? Somewhere in here, right? You're averaging over this point. What I'm phrasing on, and something we'll keep coming back to, is you have to keep bringing back your analytical technologies. So exactly what I wanted to start off today with, too, is your measurement is one part. That's not always ground truth. Your speed is going to be dictated by how you're doing the measurement, the sensitivity of that instrument, the precision of that instrument, the error on it. All these things have to be put into in your head. And again, why I'm trying to flag this is the kind of critical eye you have to build up when you start looking at literature data. When somebody gives you something and says, well, that's my curve and it's absolutely ground truth, maybe not. You know, there may be cases where if you've just been told, rule of thumb, oh, I take 4 scans on my NMR and then I get a concentration, then you go look at it and say, well, my reaction is changing at half a mole a second, this was probably not a good way of doing that measurement. You'll still get a number out of the system. The instrument will faithfully return a value. Put on your BS hat, right? It may not be giving you the right point. But generally, the practice that we try to say is we focus on initial rate measurements because that is the part of the case where I'm probably sure I know what I started on. You have low error on what that initial value is. Also, we're doing this. The earliest part of the reaction, most simple reactions, product has not built up yet, so we haven't really got any confounding things like catalyst deactivation. My product is inhibiting it. Whatever makes reactions less than perfect, like no reaction looks like this, right? There's always other chunk going on here. All that happens over time, so we're basically focusing on the early part of the relationship where everything is amazing and beautiful and, roses. That's generally what you do. Everybody should be familiar with this kind of nomenclature, right? If I start an experiment, certain trial, and I measure my initial rate, all I'm really doing is taking a tangent of that early event. I'm taking a concentration 0 and a concentration x at some time point, and based on those two initial different concentrations of A and B, I measure a rate. Remember, this is how much product is formed in some small slice of time for this one reaction. Boo, I knew that was going to happen. We're going back to the meat thermometer for my pointer event. So what I mean is, these are all three different experiments. That is not surprising to anybody, right? In order to extract a rate or an order from three different experiments, we have to run those as three different trials. Those are unique experiments that we have to run, and the biggest challenge we have to do this is all three of those need to be faithful replicates. The thing that changed between them had better only be this, right? The concentrations that you actually went through. But take me through this. How do I use these data to actually get my rates, my orders, for example? What do I do from here?
Take the ratio of the rate equations.
More words. What do you mean?
You can take the ratio of the rate equations for both.
Okay.
And then because the concentration for one is the same, so B will cancel out, A will be there, then you can take the log and solve for N.
Okay, what you're saying, that and that can be compared to each other in a binary way. This was controlled, right? This changed. The rate also changed. So we now know that at least changing A does something to rate. We know it's positive, right? You don't have to go to any log or anything else. It's actually even simpler.
Double here, but
Yeah, but yes, the full mathematical one is look at how much one changes by. The reason why I'm saying that, but yes, in the end, it's isolate the changed concentration you have here and its responding value, and then use that as a way of extracting the exponent. So in this particular case, it's first order. Sorry. This one we've got doubling this doubles the rate, right? If we then go through a binary comparison of those two, I'm doubling this one, it also doubles the rate. I would read this out as it looks like it's first order in both of the two components, right? Not weird to anybody else? Sounds good. Again, the main thing I want to focus on with those two parts is this is three separate experiments that you're going to run through. You have to have good controls as you go through them. You have to know that these concentration changes are actually being impacted. And everything is done by a binary comparison between two experiments. You're not taking a single reaction and extracting rate constants or rate values from that point. You're taking a comparison among a set of different reactions. So you have to create a matrix of experiments, and you're using this one-to-one comparison across a series rather than taking a single time course curve and extracting the rate constants and values. So that's a way that we've gone through. Again, we'll talk through some of the difficulties and challenges with that. The assumptions that we led at the beginning are the biggest things that get challenged. We're assuming that we know the concentration. We assume that there's no perturbations in the concentrations, that the reaction is most simple in those early events. And there's a lot of reasons why that doesn't actually hold. Overall, we're saying rate is a change over time. And remember that rate will happen rate will look different as the reaction goes through if it's responding to a concentration of some component. So in this case here, as A is being used up, the rate is going to get smaller, right? Each of them is expressed as a dx over dt, excuse me. So we have different tangents at those different points as we go through. The rate gets slower as we go through this, as we look at this particular case. Has anybody seen cases that looks like that? There's cases where things go sigmoidal, right? There's things where every other shape that you can possibly imagine is possible in these cases. So this is an example where if I tried to do this, if I had an example like this, give me an example of how you might use the method of initial rate on something that looks like that curve. What's your practice? What do you do?
I think you would have to wait until the reaction actually starts, because otherwise you're not really measuring when the reaction is productive.
Okay, so your suggestion is, I will, this time here, even though I started the reaction, I added a catalyst, I started heating, everybody that needs to be at the party is in the thing at that T0. You want to wait until there is a change, and then you're going to take a tangent, like a dx dt at that point?
That's my thinking, because I guess from the standpoint of making a product, if you haven't made any product, the reaction hasn't started.
No, totally. Again, first off, there is no right answer in the context of what we have now. Like using what I would first put out is, and this is what I get to do every time I review a paper, anybody who uses the method of initial rates on this one should be shot. You can't, right? Because this is like, you can approach a reaction like this, but let's say I had two time courses, left and right, and I tried to use a method of initial rate to compare something that looks like this versus one that looks like this. The quick answer should be, this is apples and oranges. Please do not do this. This is an inappropriate use of your early development. That's not a good thing to do. There's a lot of problems, because even back to this, you're right. From a mathematical definition, if nothing is happening and then product forms, d product dt really only has meaning at that point. Before that, it's 0, 0, 0, 0. But what if, instead of this, what we've shown here, you see there's actually starting material being used up. So there is a rate, starting material is being used up, there's just no product yet. So there's still something happening, there's still a change. You know, even if we can't measure it, there's something happening under the hood because you didn't do anything else. Catalyst could be building up, pre-catalyst activation. There's lots of great reasons we can talk about why a sigmoidal curve like this. And that's where it gets really into dangerous territory, because if you're trying to say, I am going to define the earliest part of the reaction where my initial rate is seen, it really comes down to where you want to put your ruler, right? This is where it gets difficult, is if I'm going to try and even look in something like this, if I was going to go into that region, let me just, clear pen markings. If you had a sigmoidal profile, there's a decent chance that if you zoom in really close on the axis, you might see a little bit of product, and then it starts to curve, and then it starts to increase. This whole region here, as you're getting this rising rate, is kind of arbitrary of where we go through it. Rule of thumb, if you look at some of the old kinetics books, is find the linear part of the curve. As some of you might know, the more you zoom in on this, and if I only have 2 data points, that's linear. You know, this is where the point I'm trying to highlight here is, when you see stuff like this, which happens all the time, don't just fall back on first principles. This is where you have to arm yourself with better techniques, and this is where modeling really comes in. Kinetic modeling using a technique like opacity is the way to start to deal with this, because there are rational reasons why a reaction does this. It is a lot better for you to build a synthetic version of that reaction and play with it, rather than saying, oh, I'm going to draw a line on this and call that my initial rate. That's open to interpretation. It's very difficult to try and make conclusions based on something that just looks that simple. Any other comment, question on that? Has anybody ever run reactions where this is normal? Like, you've seen this? You've seen it. Anybody else seen things with like long induction times before they kind of kick off? Autocatalytic is one. Dissolution. Product has to, or starting material has to dissolve before it kicks off. Temperature, sometimes, if it's warming up before it hits like a T initiation. Pre-catalyst is a big one, right? Where you need to get deligation. Photocatalysis, you have to build up a concentration of intermediate. There's enzymatic. This is usually common, where you get a pH that has to buffer in and stuff first. it's way more common than you thought, right? And I think this is kind of one of the reasons why I got into playing with kinetics, is you start to see this everywhere. So overall, the actual rate is what we get, and again, the pre-exponent term of it, or the ratio term, excuse me, here relates to the mass balance. That can come from your stoichiometry. This one here has to come from your experimental orders, and again, it's going to be a binary comparison as we go through them. That's our rate equation, which allows us to say at some known concentration and some rate constant, how fast might it go? And this is where you would use this in engineering capacity to figure out how long you might have to wait for a reaction to go through. This is probably what you've most normally seen, right? The derivative rate laws, dx dt, is kind of a single shot what's happening in a system. The ones you're probably more used to seeing is integral rate laws. This is where we draw a first order reaction, or a first order process has this mathematical form. You guys remember this from first year? You're saying that, look, if I have a reaction which is rate of product formation over time, dx dt, and that's the rate law that also expresses rate over time, this is specific to a system that has only A as your responding component. If I go through and do my algebra, I go through and do my calculus, I can derive this rate equation from this one. And again, this is only true for a nice, clean, well-behaved first order reaction, right? You guys remember what you used to do with this in first year, right? If you have this first order rate law, how does this help you? What do you do with it after this? This is your graphing thing, right? Now, the reason we set this up in this way is because it looks like these algebraic manipulations to get to your first order. The reason we use it is this, right? It's a way of linearizing data. So in general, a first order process, and again, the thing I want to emphasize here is that statement. A first order process will have these characteristic features. The plot of concentration versus time, first of all, the rate will change, right? As you're using up A, the reaction will go slower. So there has to be a responding point where the rate is highest initially and slows down over time. It's responding to the concentration of A. The shape of that curve will look exactly like you see here. It's this exponential shape. It's a very common one. People have mostly seen this. Like this, what I mean by this shape here is if it doesn't rise too fast, it doesn't look like a hockey stick, you don't have sigmoidal behavior. That's a very common mathematical function that you guys have seen before. And because of that very simple rate law, you can derive the first order rate equation in integrated form, and it's now in the form of y equals mx plus b, plotting the logarithm of your starting material versus time, that's what you're extracting from your thing, will give you a straight line. That is a normal representation that you guys should be used to. That extraction comes from one experiment, right? In other words, I can run one experiment, I can get the concentration of A at many different time points, I can throw it into Excel, I can take the logarithm of those concentrations at those time points, and then I can graph ln A against those time points, and I should get a straight line. I put a fit on it, I throw it into Excel, and I asked it to get a value. And why that's useful is the slope of that line will get me my K, right? Negative of the slope will give me my rate constant. It's a very fast way to extract this, and this goes back to now I know the rate constant. This is something you guys have probably executed. Do you know why we did this? Like, why was this the way people decided this is what people trained everybody into doing? Historically, this was what everybody was trying to do, is put things onto a piece of paper and put a straight line through it. It's because we didn't have computers and we had straight edges and graph paper, right? Like turning things in straight lines is very useful because it's a way of taking complex math and extracting meaning without having to do other complex analysis. You guys live in the age of ChatGPT, Excel, whatever. You should free yourself of straight lines, right, is basically what this comes down to. And why this is damaging, and what the thing I really hate about this sort of approach, if I had a reaction now, let's see if I've got it here. Yeah, let's look at this one. I've got a reaction. A, B with catalyst makes product. And if I go through and measure the concentration A change over time, I get this curve. I measure the concentration product over time, I get this curve. So far, graphically, these are responding to the concentration of A, it looks like, right? As the reaction of A drops, product rate is decreasing as well too, so that's starting to sound like we've got that same process as before. If I started a reaction where the concentration of A and the concentration of B is exactly the same, I can now mathematically create a curve that expresses concentration B over time, right? If I knew that the initial concentrations were the same, what I'm saying is the initial concentration of B should be the same. So from this, what do you expect that to look like? What is the curve of dB versus time going to look like based on the information you have over here?
Exactly the same as dB/dt.
Right, why?
Because, so if you have the same starting concentrations and they're reacting with like a one-to-one stoichiometry, then like every molecule of A that is consumed to form P has to also consume B.
Right, so you're going to mass balance. You're saying if that equation is true, this is a shopping list. 1A plus 1B must make product, right? And we remember at the beginning we said dA dt must equal dB dt if that's true. And then their consumption, the rate of consumption of A must perfectly match the rate of consumption of B, and the rate of formation of product must be the negative of those, right? The value, the sign will change. So formation of product must equal to consumption of either A or B, not the sum of the two, right? dA dt equals minus dA dt equals plus product, d product dt, right? Good. So what we could do is we could say, I could draw another curve that's going to be sitting right on top of this. That's going to be by dB dt, right? So we can do this in Excel now. Okay, if I took my dA dt curve and I graph it, I get a straight line. So what's the order of this reaction in A?
You don't know.
That's the right answer. You don't know. Why is that true?
The overall order is 1.
The overall order is 1. All we're saying, remember this graph here, all this is saying is that in one experiment, I measured how A changed with time. That's what this curve is here. And because of this stoichiometry, we now know that A changing with time must also equal to B's change over time. That's why these two curves have to overlap. If I take just that one curve and I plot the logarithm of A at those time points, I will get a straight line. That just means that the process, the overall reaction, is following a first order process. It is following this mathematical relationship. I don't know who's driving the bus, because as A is consumed, the reaction slows down. As B is consumed, the reaction slows down. I don't know if A or B is the one that's responsible for this yet. With a single experiment, you cannot extract orders right from this. So this is where back to first and second year may have lied to you or oversimplified. This graph only tells you that you have a process obeying first order kinetics. It does not tell you it's first order in A or first order in B, even though I happen to graph this as my ln of A, right? It doesn't extract order in that because there's two components that have to react, right? Does that feel comfortable or like? It's because, and again, I go back to this and it's kind of funny, but the number one thing, the reason I get to reject kinetic papers is people will do this treatment. They'll run one experiment, they get a graph like this, they make this graph and go, oh, it's first order in A, and it's first order in B, because I can create my ln B versus T from this one and create a graph that looks like this and happens to be straight. It's first in both. If it was first in both, what is the overall order of the reaction? That has to be. It has to be 2, which means this frickin' thing shouldn't look like this anymore. Yeah, please.
What are the effects that cause these sort of fraction orders? Is it like increasing the Lewis basicity of the matrix?
It's the mechanism. All we're saying is, if there is more, if this was a single unimolecular step, there is no way for this to have any fractional order. If this was like an SN2 reaction, it must be first, single transition state product. That's awesome. That will be a simple second order reaction every day of the week, right? If A and B go play with a catalyst and there's a whole bunch of intermediates, you can hide orders, because what happens is if A works with a catalyst and I change the concentration of catalyst, I've got a buffer. I've got a spring constant now that's basically soaking up the impact of changing A's concentration. So I'll get an intermediate that's holding on to some of A. So changing A will have an effect, But the real thing that's running the bus is the rate limiting step of that intermediate going on to product. So it's no longer linear. And that's what we'll get to with steady state, is when you actually take multi-step kinetics and you show this as a proper power law, like a fractional one, depending on what the size of those individual rate constants are on more complex mechanisms, that's why you get this. So in the case of this, all we're really saying is, if it was truly first order in A, it just means that B is not involved in the rate limiting step of whatever this mechanism happens to be. That's the only way this could exist. But it happens very common. But this sits well. Please, nobody ever do this. That one-ray experiment cannot extract rate constants from, rate orders from multiple components. You have to do this by binary comparison of multiple experiments. So when you analyze this one, let's say we took this reaction here and we said ln A versus time gave me this profile. What do you conclude from this? What is this one experiment telling you? Is this a first order process? And that's all you do. Please stop there. Because what I'm highlighting here is, all this is telling you is that there's not a linear relationship between a ln starting material and time. It's not appropriate to go, well, actually for this region here, it's first order. No, it just happens to be straight there. That is not mathematically or mechanistically relevant in any way. So this goes back to what I was saying about the sigmoidal thing. Stop trying to find straight lines and draw straight lines through them and extract meaning. Does anybody heard about the flying spaghetti monster? Okay, a couple head nods. It's funny. There's this great internet meme. You should go check it out. It's the cult of the flying spaghetti monster. One of the things they talk through there is basically the people conflating causality with correlation, right? As an example, if you plot a graph of the number of pirates that are in the world and the global average temperature, pirates are going down and global average temperature is going up. So clearly, global warming is caused by the dearth of pirates on the open sea. Just because things line up on a graph does not mean that's why it is. So this is the same thing you're doing here. Finding a linear part of the curve on a ln A versus time curve does not mean it's first order in that part of the reaction. That's an effect of whatever the equation you're trying to draw is. So if we have to balance this one, order in A and order in B, trying to go through this point is what we just discussed through. In order to do this part graphically, what we're going to have to actually do is go through more than one experiment. We're going to have to go through and run another experiment where we change the concentration of B and see how that impacts the reaction. We're going to compare between two experiments in order to do this one. All right, second order, same thing, same math. Really, this is just the same grind. The 1 over x is just a function of, this is the algebra that you're dealing with in this case. One of the things to mention, again, you may have seen this part as well too, is there are two different ways to show this equation, right? And this is just falling out of the algebra. Because the rate of change, the rate of consumption of A will be twice as fast, because I'm using up 2 A molecules, depending on how I'm viewing this reaction, from the perspective of consumption of starting material or from the perspective of formation of product, my term right here will look different. So with respect to the formation of product, I am actually graphing 2K1 versus T. And from the consumption of starting material, it's just KT. In the end, that K and that K are talking about different things. They're related to each other, right? Because in this case here, I'm saying that the rate of formation of product, because remember, it's the tangent as we go through this, must be multiplied by 2 in order for this equation, this equality to work to each other. A is being used up faster than product is being formed. So my K value that I have between the two has a relationship between each other. I bring this one up because, again, this is one of the things from, I used to teach 123. This broke people's minds because what they want to tell me is, what is the equation for a second order? Well, these are both true. What do you mean they're both true? Which one is right? This is a perspective thing. Rate of formation of your product is one way to express a reaction. Generally, again, people say, rule of thumb, it is always best to define things in terms of concentration formation of your starting material, using up starting material, because generally, that's the thing you can control. I had it, I held on to it, I put it into a reaction, and I'm watching it go away. So a lot of the times you see people say this kind of K2 versus T, the experimentalist, is what people will sit on. The other reciprocal argument is, well, I don't care how fast starting material is going away. I did this reaction because I'm trying to form my product. This definition is more important because it's actually forming the product I want. But these are why these kind of arguments exist, is because of just different perspectives in a reaction. So the point I'm trying to make on this one is there's no solid truth. When you say that K of a reaction is a global constant that you're going to hold on to with, viciously, it depends on what you're measuring. If you're watching the reaction from the perspective of a product, that may be after many steps in a reaction, compared to watching it from the starting material consumption, that's before other intermediates are being formed, and they may not be equal to each other. They're answering different parts of the mechanism of the question that you're dealing with. So then again, same part. Generally, visually, you can see that the concentration versus time curve in a second order or higher order process has this bigger hockey stick kind of shape. So that's something you want to titrate your eyes to. If you see cases where there's this rapid using up at the very beginning and then this long sort of part, those mean that there's a higher order or higher concentration response. For anybody who's done this on like TLC, you may see this where the reaction kicks off like a great shot and then suddenly it's crawling in those later phases, and that's just an indication that there's more than one species or there's a higher order response to the concentrations you're dealing with. But that's the main visual difference you're going through. Other than that, this is our constant one we run into as well. This is the concentration, 1 over concentration in time is what we're doing as our integrated rate law. Yeah, pseudo zero, pseudo first. What I mean by this, remember, is in general, if I had a reaction that looked like this, experimentally, the rate law, if I go through and do individual experiments, it has to be first order in A and first order in B. It means that the overall order of this experiment must be second. And again, a very common reaction that would follow this would be an SN2 process, right? Your nucleophile and your electrophile both will be nascent, and if they have identical concentrations, you should get a rate law that looks like this. There's only one intermediate, it's a single elementary step. This kind of goes back to that shape we just talked about, though. This is one of the reasons now where you can see when I normally run a second, like an SN2 process, I usually hold one component in very high excess. Why do I do that? Well, from a mechanism point of view, this is helpful, right? If I take one of my species and I have it there at 10 times the concentration I need, I can isolate the impact of the other thing. If one thing is low concentration, then it's useful for mechanism. I can compare and say between different nucleophiles, one is better or one is worse because I'm removing the impact of whatever that other species is. So holding one super high or low, I can basically say that the relative change in concentration of one of these components is effectively 0. I can make it go away, and its concentration is now constant. Its impact, whatever that concentration is, now becomes part of my K value, right? It's a constant in the system, so it just gets binned into the K that you're extracting. The other reason we do this practically comes back to this. If that's where my time is and my time is money, I don't want to be waiting here. If you have a second order process, a very common way of fixing this is we just increase the concentration of one of my components that's easy to remove so that I can make it act like this instead of waiting a year and a half for the thing to actually sort of go and finish. Those last couple reactions where two species are trying to find each other and they're both very low concentrations is very, very painful. So this is where a practical element of this part comes out. Yeah, so this is just that latter part. If we're doing this and we hold one concentration super high, that's where we're getting this artificial removal, or basically the rate constant here reduces to something where it's now the concentration of B in this case, if I was holding it very, very high, it's now being impacted or stuffed into this rate constant. So the punchline from these last parts, even though we talk about Ks as being almost like temperatures, or not sorry, temperatures, melting points. A lot of the times people treat Ks as colligative properties, right? They're like something that is specific to a molecule or a system. It's a fingerprint, it's an identity. The point is, depending on how you ran the reaction, your initial concentrations, your K will, the K value you extract for it is circumspect. The underlying K for any process, if we're never changing these two, let's say we're talking about an SN2 process for how does chloride displace triflate. That will be something that has a direct underlying K. But depending on how it was run, if you're running it under different conditions, different temperatures, different components, what you're actually going to measure is going to be something more like this, where there's convolution that's associated with it. And this goes back to if I'm looking at this with respect to the product or with respect to the starting material. How much does this feel like review and like sweeping off stuff that you'd hope you'd forgotten? Nod, nod. Important because, again, the main thing about this part too is that as we go through these are things that you're going to impact and see through. First, second, and 0 are the main ones that you're going to see, right? 0 just means there is a change that's happening. The concentration versus time process is absolutely 0 order. It means it doesn't really care what the concentration is. It's just happening. It's only moving according to a constant. So now that we've got those three, if you had to have what you'd consider an emblematic reaction or process, give me something that's emblematic second order. We just talked about it. What is a definite, put your hands on it, you know it's going to be a second order process. That would be SN2. What about first order? Emblematic first order process. What's something that you guys know for sure should be a first order process? SN1 asterisk. Has anybody run an SN1 reaction? Yeah, there's a good reason why they suck. Carbocations do not like playing with other people and stuff, right? But so I want you guys to get in your head what you could put your hand on. Yes, I guess theoretically SN1. It's not something you go to the lab and do. Do you have a zero order process that you'd put your hands on and say that is absolutely a zero order process? Something that does not respond to concentration. Okay, so that's the homework I want you guys to pick up on Friday. What's that?
Maybe a decomposition?
Think about that. That should be first. So that's the piece I want you guys to come with. I want you guys to come with what is my absolute time in the bank first order, second order, and 0 order process. Okay, see you guys on